Assalamu alaikum everyone. I'm Ms. Bendjilali Hadjer, PhD student at University of Sidi Bel Abbas. My presentation is entitled The Structural, Electronic, and the Optical Properties of the Double Perovskite Compound Ba2MgWO6 using density functional theory. This presentation has four outlines. Firstly, the introduction. Secondly, method of calculus. After that, the results and discussion. And finally, a conclusion. We start with the introduction. We have need to know some details about perovskite. So what is it, perovskite? Perovskite is the name given to a whole family of materials that have the same basic crystal structure to the oxide mineral calcium titanate, CaTeO3, which is the first discovered in the Ural Mountains of Russia by Gustav Rose in 1839, and named after that in honor of the Russian mineralogist Lev Perovskite. But the main aim of this presentation is to discuss the physical properties of the double perovskite, how we can obtain these compounds. The answer of that is by doubling constituents permits to the possibility to form the double perovskite. So the double perovskite materials attract a huge attention by the researchers due to their remarkable outstanding optoelectronic properties like tunable band gap, the high absorption, etc. These compounds are suitable for the practical devices, can be used in different applications in technology like semiconductors, lasers, and solar cells, etc. We pass to method of calculus. The main objective of this study is to expand researches about double perovskite compounds. Our contribution in this domain is investigated about physical properties using the DFT, density functional theory approach. DFT belongs to the family of first principle ab initio methods, so named because they can predict material properties for unknown systems without any experimental input. And the principle of using DFT is to find approximate solution to the Schrödinger equation of n interaction electrons, or the problem of n-body. And all of that after many approximation equations and methods. Here in the framework of DFT, we have used the full potential linearized augmented plane wave method FPLATW, implemented in Vien-2K code using GGA gradient generalized approximation and the modified Bank-Johnson potential, with using the data for each atom of this data for each atom of our compound. To the results and discussion, in the first we calculated the structural properties. The geometry of our compound is optimized by calculating total system energy at different volumes. Then the obtained data energy volume are fitted by Birch-Mennager equation of states. The equilibrium volume is that corresponds to the minimum energy. The calculated structural parameters such as the lattice constant and the Burke modulus of considered compound are given in table 1. It's seen that our calculated structural parameters are in good agreement with the experimental value and the theoretical data. Using the respective optimized structure, the band structure of the double perovskite oxide is computed along high symmetry directions from W to K in the Fermi in the energy range from -5 electron volt to 8 electron volt with the GGA approximation and MBG potential. The Fermi level is set at 0 electron volt, presented in figure 2. The figure shows the semiconductor nature with the band gap at gamma point for the maximum valence band and X for the minimum conduction band gap. The total and the partial densities of states, TDOS and PDOS, of investigated material are calculated and presented in figure 3. We remark that valence band is predominated by orbital P of Mg and W, and sp states of O, oxygen, and for the conduction band is mainly predominated by p states of Ba, barium atom. Going to the optical properties from the figure for important optical responses. This compound is promising candidates for optoelectronic devices in the visible and ultraviolet energy ranges, since it is an indirect gap material that possesses properties of a direct band gap material. Finally, we conclude all of that in two major points. That our compound has an indirect band gap, or like we name it, a pseudo-direct band gap. There is little difference between the direct and indirect, the values of direct and indirect band gap. The second one, that our compound is an indirect material that possesses properties of direct band gap materials. So it is a competent candidate for the optical devices, including photovoltaics and solar cells. And thank you for your attention.